All right, we might start. Hello, everyone. My name is Matthew Greenwood, and I am manager of regional compilations in the minerals team at the Geological Survey of Queensland. I'd like to begin today by acknowledging the traditional owners of the land in which we meet today. For me, in Brisbane or Meanjin, this is the Yagara and Turrbal people. I'd like to pay my respects to elders past and present, and I would also like to extend those respects to any Aboriginal or Torres Strait Islanders who are online with us today. Today's presentation is from Steve Bowden, who is the Principal Data Manager of the Geological Survey of Queensland. As a bit of a departure from our normal webinar series, Steve is the only presenter today. He will talk for about 45 minutes and then we'll have some question time afterwards. Steve's presentation is on subterranean syntax, envisaging a machine-readable Earth, or as Steve has told me, knowledge graphs. If you have any questions through the presentation, there is a Q&A question box at the bottom, and we will ferry those questions through to Steve. And then at the end, we will open discussions for any other questions that may come up or discussions to continue on after the presentations. So please join me in welcoming Steve in his presentation.
Yeah, thanks, Matt. Thanks for the intro. I'll just put my screen up. Can everyone see my screen?
Yep.
Great. Yeah, so as Matt said, this presentation is about knowledge graphs that we want to get towards that syntax for describing what happens under the Earth, and how do we get that geological setting described in a machine-readable way, so we can leverage that powerful compute capability that's coming just around the corner. It's already here in many ways. So yeah, this webinar is essentially about knowledge graphs. We're going to cover two core areas of knowledge graphs. We'll be looking at data mining. So how do you just get all your data into knowledge graphs and sort of explore that and find some insights. So we're going to cover labeled property graphs as the type of knowledge graph used for that. And at the other end of this webinar, we're going to look at machine-readable descriptions of geological settings, which is applying that more formalized approach to setting up graph networks. So semantic modeling overview, we'll just talk about some of the concepts there, how you integrate system models with factual data, and what kind of inferences we can make when you apply that more formalized approach. So they're the two things. This is a longer presentation than I usually do on knowledge graphs, so it's a really good opportunity to get into the weeds a little bit and learn a bit more and give you something that you can take away and practice. So yeah, there'll be two types of knowledge graphs discussed, as I mentioned earlier: labeled property graphs, which are your nodes and edges, which I'll go into a bit further later, and RDF triples, which is the subject, predicate, object ones, which I'll cover a bit in a bit more depth later. That's just high level, two types of knowledge graphs. There's other types out there, but these are the ones that we're currently looking at. Knowledge graphs in general is essentially how a thing relates to another thing. It's that simple, and the graphs themselves is a way of representing that. So for example, Alice is friends with Bob. That's just, we have Alice as one thing, Bob's another thing, and the relationship is friendship. Alice fixes computers, Alice is a thing, and computers are things, and Alex, the relationship is her ability to fix it, et cetera, et cetera. So you have this network, this knowledge graph where Bob owns a computer as well. So in this knowledge graph, simply you can make inferences and you can determine things from that. So we can see here that if something goes wrong with Bob's computer, there's an avenue through Alice to get his computer fixed. It's one of those, it's a simple, very easy to understand, human relatable concept, these knowledge graphs. So labeled property graphs, they're sort of a very simple data structure to describe that. It's very similar to what we've had before. Essentially comes with nodes and edges. So nodes are your things, for example, people and places, and it has edges, which are the relationships between the nodes. Strange word, edges, but that's just the way it is. So here are your nodes. So we have Bob, Alice, and we'll put Brisbane in there as well. And the edges are the relationships between those. So Bob lives in Brisbane, Alice lives in Brisbane, and Bob's friends with Alice, and Alice is friends with Bob. And then they've got the properties. So the edge properties and the node properties are attached to those nodes. So Bob can have a surname, Alice can have a date of birth, and they can have been friends since 2014. So that's the property of the edge. So how do you get to that point where you have knowledge graph data? You can always take your metadata, which is done quite often because metadata is sort of graph by design, or you can convert your tabular data into knowledge graphs. But if you've got unstructured data like this is a little snippet of text taken from the Queensland Geology report about coal. And how do you get knowledge graph out of this? You have to go by hand and pick out all the particular words and find the connections. It's quite challenging. If only there was something which was developed in the last couple of years which could look at some text and do things with text. And fortunately, we have AI. Came out a couple of years ago, ChatGPT, we all know about it. And in terms of data mining and just grinding through text and returning a knowledge graph, it actually works quite well. You could even ask it just to give me a knowledge graph back out of that text. But over time, I've sort of developed system prompts. So you can sort of see down the bottom there, that's just an example of the size of prompt I'd be using to get a knowledge graph out of that text. Because if you're doing this at scale, you're doing it thousands of times, you might be paying for the API to do this. You really want to get the most bang for buck and most consistency. So you refine those prompts. So just so you have an idea of what kind of prompt goes into getting a knowledge graph out of some text. That's an example. And from that, it generates a graph. I'll just hop into a...
Hey, Steve, while you're just jumping between, that thing at the bottom, the floating thing that's saying app zoom is sharing your screen. Can you see it right there? It's just showing up and now people can read your screen. Thank you, mate.
Perfect. Yeah, I didn't realize that. I thought it was only for me. All right, so this here's an example of that piece of text about coal from the geology. This was the knowledge graph that was generated out of that text, just using AI, no extra effort to control it. And you can see here are the nodes. It has properties on those nodes. So this is an open cut mine. You got coal, it's metallurgical and thermal, and those those edges also have some properties assigned to them as well. So within that, you can process it and convert it into structured data that can be worked with. So let's hop back into the presentation, and I'll hide this thing again. So I sort of see it as a low risk play to reduce that time to value, because you've got lots of data, we want to work with it, and sometimes going into data can be a high risk activity because it takes time. You think, well, if I have to go through 1,000 reports, it's going to take forever. How do I accelerate that to see if there's anything worth pursuing, just to give that little nudge in the right direction? This is one of those options where you can just generate knowledge graphs at scale, and you can even apply generic modeling approaches to it. So you don't have to have a specific idea as to how things fit together. You can use the basic grammar of the English language, where you can assign the nouns in the text as nodes, the verbs as the edges, and the adjectives, since adjectives describe nouns, can be the node properties, and the adverbs, since adverbs describe verbs, can be the edge properties. And something as simple as that can direct an AI tool or something to carefully put together that knowledge graph for you. So that's a very simple way of getting everything. So you can cover large reports just through iteration and or some sort of recursive function to move through, and you can aggregate all of those outputs at the end, because you're going to have the same similar names, similar concepts being generated along the way, and they can all just stack upon each other at the end when you can form all of those mini graphs into one giant graph at the end. You can also cover multiple reports using search engines. So this is another way. So say you would use a search engine across a bunch of text documents using a keyword, and you can pull back maybe 25 results, and then you have snippets of text from each of those results and some associated metadata with those results. You can blend all that text and metadata together, generate a knowledge graph, and then you have a graph that covers multiple reports and connects things like the authors and the concepts within those reports, and you might find something there as well. So it's very flexible. You can work different data types, so you can bring CSV data into the knowledge graph, you can bring text data into the knowledge graph, along with even potentially image data if you're using some labeling or AI to pick out features from the images. You can bring it all together in that one space. And also different data contexts. So your analyses can mix in with your company reports, which can mix in with something like academic publications. Obviously, you're involving AI, so there's a drawback there. accuracy. So, you can't put any stock in the numbers that come out of some of these things. It might find something and be out of context with values. So you be very careful there. And also the consistency of terms. Since you're using an open schema to develop the graph, you might have very similar terms that have been separate nodes where you think they should be the one node and it's gone and made them separate. So you're going to have that issue. And you can also have unintentional aggregation on the properties within the node. So it might have contradictory properties because it's moving across data, which says different things about the same node. Like say something like a particular rock type or lithology type was described as being pale blue in one and pale green in another. They're sort of contradictory because there's two different colors there. So I'll just show you an example of how this would apply to, say, a well completion report, which is a common report we find on our open data portal. And they're just shorter reports, so I can run this process through and we can see what would happen. So let's just hop across into the next screen. There it is. So this is a knowledge graph of that well completion report there. And you can see it's got in the well completion report, there's a section about geological settings, and you can see how it's sort of grabbed the geological setting there and found a lot of connections between the Great Artesian Basin, the subgroup range, and structures and faulting, which is all pretty good. But I did find something interesting in this one. I'll just see if I can dig it out. Where is it? There it is. I found it managed to work through and get. Let me just get this up. There we go. Let's see if I can get this into shape. All right, so you can sort of see how it has the lower part comprises coarse grain, mature sandstone, which grades up into labile sandstone, grading up into siltstone, grading up into mudstone, which is grading up into coal, which is all pretty cool. So it's able to, just from that crude prompt of digging through the data, it's able to formulate that more detailed lithological, sequence in that profile there. So that's pretty interesting. And that was just a simple application of a basic prompt saying, give me the verbs, the nouns, the adverbs and adjectives, put them into a knowledge graph as you move through this report and stack it together. All right, so I'll hop back into my slides. And I'll just hop into another example now, which is you looking at search keywords. So I'll just load this one up. Report visualization, perspective. So what I've done, I don't know if you guys have seen this before, but we have a GSQ Labs place on GitHub, which is just a hosted page on GitHub where we can put some tools, and we have our industry reports, about 85,000 industry reports, which have been OCR'd. And so the text is available and has been indexed just using a normal type of indexing tool, search engine. And from that, when you search a term against those reports, so say we're looking for the term prospective mineralization, you'll get some results back and you can scope that into a particular area. So I've just picked an area of Mount Isa here, and around Mount Isa, and looking at results that contain text reports that contain those words, prospective and mineralization, in the chunks of data that have been indexed. So there's 19 results in this particular search. You can see there's metadata that goes against it, and then within that chunk, that snippet, you've got all this text, the snippet of text that it's using to find those search terms. So there's about 19 results here, and I think in the example I've got over there, and on the next tab I'll show you in a sec, I think there's about 13 results. But you can see these are all the search terms for that given area which contain those keywords. So we're going to mash these chunks of text together and put them into a knowledge graph. So this is it here. I'll just see if I can pull it up a bit closer. It's a bit hard to look at, obviously, because there's a lot of text, and you can just imagine when you're dealing with real practical sized data in graphs, it's almost impossible to look at it this way. It's really pretty for demos and examples and showing the concepts of graphs, but when you're working with them, you've got to learn to query. You've got to get down and dirty with the query languages to pull things out. So this is, as you can see, the green lines here are connecting company reports, and they're connected by a permit. So that's a bit of metadata there. EPM 11524, these reports here all have the same permit. And you can see the red lines are connecting the concepts with the reports. And the blue lines here represent the author, and the yellow is the date of the report. So there's a few reports in those results for that particular area. And what we're going to do is say, all right, well, this is my graph that I'm looking at. How do I go a bit deeper? How do I get some insights out of this? So I want to look at this, say I want to look at the copper mineralization. So this is a term I'm interested in. So here's a node. I'll click on it. I'll try and just pull up a subgraph of this term and see what it relates to within my little knowledge graph that I've got here. So I should be able to create a view, see if this works. We'll stick it at number 10. And we're just going to filter on the node being copper mineralization. And we're going to go one hop out. One hop out from that node. This should pull up just that one term, and everything that comes out one relationship out. So one friend of a friend, 1 degree of separation from the word copper mineralization. It's quite interesting because you've got a few interesting things here. You've got there's 2 reports where it's mentioned in. You've got a geochemical survey that it relates to. There's a company that appears to identify something relating to copper mineralization. And you've also got some a geological formation there, the Cibella granite complex that's connected to it as well. So that's quite interesting to see how from that, you pull back a graph from a set of information, multiple reports, and then you can then drill down inside that graph against a keyword that you're interested in and see what are the nearest connections to that. You can also follow a traversal path between 2 different nodes and find everything in between, or different ways from getting from one to the other, and that's called a traversal. But in this case, it's just called a one hop connection away from a node. So I'll just hop back to my present. I'll show you what we can do with that. So that's by doing it this way, we're sort of making the data, the concepts machine readable. So these knowledge graphs, these nodes and edges, they're in this format JSON. If you've done any coding, and I'm sure you've come across JSON before. And once it's in JSON, you can go and create code and programmatically work with the content of this knowledge graph. But aside from that, if you were to plug this thing back into an AI tool, like a large language model, this is a ChatGPT example. So I've just taken that raw JSON file and just shoved it into ChatGPT, and it's to see what comes out, and it is able to recompile the meaning of what was in that subgraph into something meaningful and explain what's actually going on. So it's in some way it's a form of data compression, and also it's a form of bringing the right relevant information into the context to paint the picture. So yeah, so pretty handy. And obviously these LLM services, they have an API. You wouldn't have to go and copy paste it in. You can do this automatically using an API. Obviously, data security is a major consideration here when using these APIs. So just be mindful of that. They also cost money. But yeah, there's private cloud options, or you can run these large language models locally. You will have a cost of whether it's increasing the cost. So you might have to pay a lot of money for the infrastructure in the cloud, for a private cloud, or you may have to accept like a lower power, because the value proposition of these big ones like Anthropic and OpenAI is really, they've got the big models available, so but they want your data. So it's a bit of a give and take. You got to figure out the right approach for your use case. So working with label property graphs at scale, as you can see, that small set of data, 13 results in the 13 results put into a knowledge graph. It was really hard to look at and understand, and you can't really see what's going on visually. However, querying is the predominant use case. So learning how to query the knowledge graph and store the data at scale in the right kind of databases is the key. So we have a few different databases for storing label property graphs. Neo4j, OrientDB, JanusGraph, TigerGraph, they're all well known. And Neo4j uses this open cipher query language, which is very common and popular, and it's quite an efficient way to get in there and retrieve data. Here's an example of an open cipher query that would have pulled back that one hop connection away from the word copper mineralization within that graph. So it's pulling back the node copper mineralization, one hop relationship, and then storing all those connected nodes to another element, and then returning all of those elements. So that's 2 lines of query, which you can template up in code relatively easily. So if you're working with a graph system programmatically, you can just see how simple it is to make progress and interact with its API. Another good thing is worth noting is that there's an ISO standard which has just come out called GQL, came out earlier this year, and it's inspired a lot by the open cipher language, but it's an open standard for graph query languages, which is really good if you're into non-proprietary languages and you want to apply open standards to the way you manage your data and set up your data stores. GQL is here, so there's a standard there you can look up. But yes, as I said before, an open schema is prone to challenges in data management, but all of these databases do have schema management features, but you've got to put a lot of work at the front to set up all your controls. And when you get to that point, you might be, we'll talk about RDF later, but there might be more formalized ways to deal with those problems rather than using labeled property graphs. So we've talked a bit about how AI can help generate knowledge graphs or process knowledge graph data, but it's actually the other way around as well. So AI can actually leverage knowledge graphs to enhance its capability. So if you're at the last webinar, you've seen Rob Chatterjee, our principal data scientist. I'm sure he would have talked about retrieval augmented generation RAG systems for large language models. And that's the way of pulling back relevant data into the working memory of a large language model. And so from that, that's the general of RAG. So then there's a search term there you could put into Google and you get all this cool stuff. It's called graph RAG. And that's using graph databases as a mechanism for retrieving contextually relevant information and bringing it back into the large language model's working memory. So it's a token limit, essentially. Some have 200,000 tokens, some have 100,000, a million. It varies depending on the model. If you're working on a local run model, you might be stuck with 32,000. So, you've got to kind of budget that working memory and be as efficient as possible. So anything that can bring the best information back and compress it, like a graph RAG could, is definitely worth a look. So it can take keywords from whatever input people are putting in and bring back those relevant results. And when it brings back the results, you don't have to reprocess them into English because the large language model will understand the graph anyway. So you can just give it pretty raw traversal path or a 1 or 2 hop connection to a node or a set of nodes. So that's one aspect that knowledge graphs can help this latest sort of AI revolution that's going on. But it can also go the other way around too. It can enhance the prompts that that you put in to an AI system. I don't know if everyone's used image generation tools on online yet, but there's plenty out there, Bing images and things like that. You type in you want a picture of a jellyfish. That's what first goes in, but what actually happens behind the scenes is that they'll go and take that and then they'll rewrite your prompt in such a way that will get the best image out of the image generation tool. So they do prompt enhancement at the back end, which makes it easier for you because you just type in what you want, and it goes and fills all the gaps in and specifies some of the themes and styles and whatnot for that image. So that's sort of prompt enhancement. And you can do the same with knowledge graphs. So if you understand what the customer context is, who's putting the text into the AI, if you understand their user profile or anything like that, anything you can grab that can bring more contextual information about, they might be looking for a particular type of mineral in a certain area. So you can pull back, the graph can then pull in all these relevant report IDs or whatever it is it can grab, it can throw those into the context of the prompt as well. So that can lead to getting better answers out of the the AI tool because it just knows more about what you're asking. You're not just being a bit vague with it. And not to mention, I know LLMs get all the attention these days, but traditional ML can also be applied along with network pattern matching and other data science activities can be done with knowledge graphs because they have some statistical capabilities in returning numbers and counts and aggregations. If you haven't locked your schema down, you've got a bit of a risk there in relying on the data. But yes, definitely they can work and generate data that can be pushed into some linear regressions and things like that. So that covers the labeled property graphs side of things. That's knowledge graphs in terms of data mining. And we'll look at a bit of a more formalized approach to working with knowledge graphs, because, for example, that's what this topic of this this webinar is about, which is getting that subterranean syntax, getting that description of Queensland and geology. It's not like it's going anywhere. It's going to be the same for the most part. A few rocks will fall and disappear, and some geomorphology might happen on the coast, but for the most part, the rocks that are there are going to stay there. So there's no point sort of rushing into generating these descriptions of how things are under the ground, when we can apply a more methodical approach to getting it described well in a way that we can introduce more scientific information into the model and have more reliability and quality in terms of what the kinds of queries and results we're getting out of the graph, and then can make more inferences and get more value out of it. So I'll just talk about the RDF triple store, and because this is all done through semantic modeling. On the bottom there, you've got a sentence, which is a description of a world, a particular world, in relation to cats here in this example. So we're just going to say that cats can have pet names and be inside houses that have addresses. So that's just a statement about things, no particular thing in general. We're just talking about cats having pet names that can be inside houses that have an address. So I'm not talking about your house or your address or your cat, or we're just talking about the high level model. And that is sometimes called an ontology or a semantic model if it combines, a bunch of ontologies within it. But it's just a set of rules around how things relate to one another. So that's sort of where you start with semantic modeling. You set up a bunch of rules and you can adopt different ones that are already being done. You don't have to reinvent the wheel, but that's sort of a description of the high level, how the things relate to one another. Then you want to represent data inside of that model. You can then put that data in. So you have your cat is inside your house, or your cat Puddles, its name is inside your house at 42 Example Avenue. And we actually store this data as a triple, the RDF triple. So your subject, predicate, object. Your cat is inside your house. So your cat is the subject, predicate is being inside, and the object is your house. So but to actually write it in RDF, this is where it gets a little bit hectic, is where it comes out as a URI. Reason being is that URIs are used for the internet. Internet has lots of web pages, you may have noticed, and it all seems to work. So if you can use this system for the internet, why can't we use it for data? Because data has a similar use case. You've got data, you want to be able to bring it all together. You don't want it all everything to collapse as a result of that. So having URIs, it's a tried and tested approach for web addresses, so it's applied to data. There are formats for storing this in a way that you can make it less hard on the eyes, and that's Turtle and JSON LD can help make it easier to look at and can nest things. Much easier way to work with Turtle, but still not as probably not as simple as a label property graph. So it takes a world view of graph data. It's based on the linked data initiative W3 standards. As I mentioned before, has these triples, subject, predicate, object, and you can import ontologies from global and local custom sources. So what I mean by that is that we use if we want to describe the vocabularies that we work with within GSQ, we don't need to invent our own way for those vocabularies to relate to one another. What's a broader version of a group or a subgroup, or if you want to look at sandstone being one, and then it breaks into different types of sandstones, that's a sort of a narrower thing. But I'm not inventing that myself. That actually comes from an ontology called SKOS, which is called the Simple Knowledge Organization System. And that ontology helps people describe how things relate to one another and can be organized. So there's no point us coming up with that. We just import it from that already standardized SKOS ontology, and we start applying the connections between our vocabularies using that. And that's just an example of how you can import them. There's a whole bunch. There's Dublin Core Terms. There's we use another one called SOSA, which is a way of doing results and data. And by doing it this way, it supports interoperability and reuse. You can literally combine these triple stores into one if they're following the similar ontologies, and they just start blending together without any issues. So one thing to might be mindful, though, you need to be able to validate the instance data that goes into them. Instance data being the specific things like your cat, your house, and stuff like that, and your address. So you might have to validate that as well. So there's a tool called, or a validation process called Shackle, called Shapes Constraints Language, and that language can put some rules around what goes into the triple store. An example could be, say you're doing a transport system and you have buses and you can't have more than 40 passengers in the bus. When you're setting up the graph for that, it might limit the number, the values that go into the instance to be less than 40. Or the types of buses can only be like a bendy bus or a normal bus or a small bus. There might be only a certain group of buses that you can use. So Shapes Constraints Language can control that, and a whole bunch of other bits and pieces to validate what's in the graph. So really useful. As I said before, vocabulary management, your how you describe things within your organization, the knowledge that you have, and how you can represent that in a graph. Really useful for that. And we use our total, as I said before. And because you're following all these rules and you're adopting open standards and have a systematic approach to setting up your model and then adding your instance data afterwards, you can get really precise query responses and inference outputs because of that, all the validation that goes into the data that goes into this more formalized semantic model. And Sparkle is the query language, which is an open standard there as well for getting into that data and running results out of it and doing calculations or whatever it is you want to pull back out of the triple store. Sparkle is the way you do that. So here's an example of what a total file would look like. It's pretty straightforward. So you've got just a bit of text, just a text file. You can put your own comments in. And up the top is where you kind of alias those annoying looking web URLs. And then you don't have to, once you say them up the top, you don't have to say them again. It's done. And you just use the little shortcut word that you've created there to explain it. And you can see here that we've defined our three things: the actor being inside, the your cat, and your house. They're entities. We know they're there now. And then we can set up that relationship that we were talking about before. Your cat is inside your house, and that's the triple. And that's also representable in JSON LD. So JSON LD is just, if you program and work with code, you look at this and go, this is much easier. I can work with this. And this is, and essentially you have two components to it. The context up the top, which is an object that contains these prefixes that we talked about earlier. And then you have the graph, which has the shorthand version of those prefixes in there. And then it will and it has all of the data within the graph. And that's and if you were to pull that out, you'd have to kind of grab this value and then grab the prefix, join them up, and it's all pretty straightforward in code. So now you want to query this total file. This obviously on the left, it looks pretty harmless piece of text, but it's actually a graph and you can query it. So if you want to query that, you can write a bit of Sparkle, and Sparkle is a query language designed to query this type of data, and it's fairly they're very straightforward queries. It just takes a little bit of getting the hang of. So you can select the cat and the location. So say I'm looking for where are all the cats? That's my question I have. Where are all the cats? So cat, I want to get the cat and the location. They've got to be cats, and they have to have a location. So that's the result you'd get. If there was more cats in my turtle file on the left there, then you'd get more results. But for here, we only have just the one cat, and that's the result you'd pull back. So obviously that's just the high level 101 on semantic modeling with some simple examples, but when you apply it to geoscience information, there's a lot of potential there. So here's a simple example at the geoscientific level. So we're stepping up a little bit into the geoscience, the subject matter domain of geoscience, along with semantic modeling. So I don't want to go too far into the reality of how this actually looks. We're just going to look at something a bit simpler. So we're going to look at the Northwest Queensland Mineral Energy Province report and a really high-level description of the Mary Kathleen domain, which is, I think it's a one page or 1.5 pages. There's not too much data there. So it's not too much work to go in and do a bit of a demo and mock up on what's inside of this. And I've just grabbed a little example here, a little paragraph out of that one page, just to see the text on the right here, the Bellara quartzite. And from this simple piece of text, since the geoscience writing is so densely packed with information, there's a lot you can actually get out of one paragraph of data. So yeah, it might be a little bit challenging for AI to kind of pull this stuff out. So you've got geofeatures, you've got geofeature types in there. You've got relationships between these geofeatures. You've got geological events, and you've got geological event types as well. On top of that, you've also got geological properties. So a whole range of things, of types of things, are in this one piece of text, and you apply that across these couple of pages, you get a bit of a picture. So that's the geological settings, and not only that, you can also apply it to something like a system. A theoretical system. And say we want to blend mineral systems with a geological setting and see where the overlap is. We'll take a look at same report. There's a section on there around the Northwest Queensland Mineral Province, an energy report around the copper, gold, and iron oxide mineral systems. And then you can grab different things out. So I think the main feature here, I'm not an expert at this in no way, but I can see I've got ingredients, system ingredients. I've got ingredient properties that go into that. And then for each of those ingredients, there's a particular geofeature type, which can be, is mappable, or geological property, which is also mappable. So once you get those two things, you can sort of combine, see where there might be some overlap, because I saw some common words there in that first page when we're looking at the Mary Kathleen Domain Geological Report, and when we're looking at the mineral systems, I saw a bit of overlap there. So here's a really crude, high-level geological model concept schemes here. So a little hierarchy here. So we've got a geological feature, and we've got that feature relationship type, the way they relate to one another. We've got our geological feature type, and we've got the geological properties of that geological feature, a really simplified version of a geological model. And over here, we have that system model, that mineral system model. So we have a mineral system, the level of importance of a particular mineral system ingredient. We've got our mineral system ingredients here. And we also have the mappable geofeature types and the mappable geological properties that relate to that mineral system ingredient. And I can see how there's a connection there. So we have our geological model has a bit of overlap with our system model. So worthwhile putting them together in a graph. And if it's done in a way with, in a formalized manner, you might be able to get, start building a powerful data store. And on top of that, we're dealing with just sort of some high-level text and a system model. We want to also introduce factual data into the process as well. So not only do we have the geological model, we have a system model, and to get those geological properties, we kind of need factual data. We need some results. We need some samples. We need observations and tests being done, analyses. So you can also bring in factual data into the overall graph, and you can see how a geological feature can be sampled via a survey and within a site, and then you can make observations from those samples that consist of results. And when you get those results, they can feed back to form geological properties. Right, so we have a connection between our factual data and our geological model. We have a connection between our geological model and those mineral systems. So say we've traversed 3 different domains here within the one knowledge graph, and we want to sort of see how that all fits together. So within GSQ, just I'll spruik this a little bit. We have a data model based around the SOSA. It's called SOSA model, and it's an ontology for observations and samples, where we've adopted that approach and applied it to our context. So this is our data model, where we have observations made from samples, from surveys and sites that feed back into an overall geological feature, and those observations produce results which can feed into that geological property, which are properties of that geological feature. So that's how we've structured our enterprise database, and we're feeding data into that at the moment to try and capture that and get value out of that process. And that's sort of combining those 2 sides, the factual data and the geological data, into one data system, which hopefully is going to yield more and more benefits as we move forward and continue integrating data that way. And the building blocks for this as well is our vocabulary. So we have a geologic feature type vocabulary, which is still being progressed, but that's the feature classes at the high level. You can see them here: complex rock units, intrusive rock units, landform features. So all these geofeature classes, they form the necessary building blocks for describing the geofeature types. And obviously it gets quite complicated. There's quite a lot. And as you move into areas like Mount Isa, there's a whole range of geological feature types that we're working on and building out. There's a pretty good repository there already, but we're building that out so that we can actually have the right ingredients for describing that subterranean syntax under the earth. I'll just, I think I've got time. I'll just pull up that particular turtle file. All right. This one here. So this is the geological feature type group, and you can see how it's all spent. This is how we've organized the data hierarchy. And this is your SKOS, Simple Knowledge Organization System structure, where the starts off there and it breaks out into these different things like a regolith feature, a landform feature. There's over here, we have tectonic features, and then within tectonic features, you have narrower concepts such as continent, sedimentary basin, things like that. So if you click on that, you can see all of these different connections to it. And then you see, all right, this one here has a broader connection to being tectonic feature. So the way that we've structured the geological feature types is in adopting that semantic modeling approach, using that globally recognized ontology called SKOS to describe, to set out how it all connects. And these can form the building blocks as we create those descriptions of what's under the ground, those specific things, like some sort of granite complex within Mount Isa. It doesn't have to have its own word. We can adopt it from here. All right. So I'll just hop back into the Prezo. Oh, we're into demos already. That's good. All right. So I'll just load up that example on the Mary Kathleen domain, a more simplified example. So without the factual data put in there. So this is we're just looking at a small graph from that one page of text on the Mary Kathleen domain is this top section here, and that one of the mineral systems that was in that report is shown here. So I think if you can see the Mary Kathleen domain, that's the node for that just there. And then it sort of spans out. It shows it's related to the Metacuti domain. It's got all of these geo features inside of it, which have geofeature types. And then you're looking at the mineral system. We've got the East, North, West Queensland mineral province epigenetic copper, gold, iron oxide mineral system. And that mineral system has, these desirable ingredients and highly desirable ingredients and essential ingredients. That's sort of how I've read it from there. So you've got desirable ingredient of replacement, and then related geoproperty for that desirable ingredient is being ironstone rich or chemically replaceable. And so here we've got one for, we've got a highly desirable ingredient of repeated fault movement during origins. So that could be connected to a fault zone, which is a geofeature type. And the fault zones that we have in the data here, we've got the Quamby fault zone and we've got the Pilgrim fault zone. So we can see our connections between the geofeatures that have been identified in the Mary Kathleen domain with a particular geofeature type that is also connected to this mineral system in two ways. So that's sort of where you can connect the geofeature types, but obviously the geological properties are sort of just hanging there, not knowing what to do with themselves. They haven't got anything to connect to over in the data, so we need to solve that problem. So I'll add a bit more data into the system, and we'll see how it looks then. It might be a little bit hard to understand, but we'll take a look. So it's a bit more like one of those little seeds from the plant that you blow, and all the seeds go flying away. So what we're looking at now is those little yellow dots that are circling around the model have been added to the data, and they represent the samples and observations and results that have been made on the data. I'll see if I can get a better view. There we go. So I've got this sample here. I'll click it. Sample number. This has come from a spreadsheet that relates to the Mary Kathleen domain. So I was able to find just a simple set of analyses that we can link up had references to the geofeatures they came from. So I thought this is great. I'll throw this into the data and be able to see a good example of how it all works. So this is the sample that it comes from. And there's a bit of information about the sample in the data. Looks like it's from a sample of meteorite from the Corella Formation. And within that sample, we've got some laser ablation work. We've got some XRF stuff. What we're going to look at here, we'll look at some iron oxide XRF data. So we'll scroll down here, and you can see we've got a 2%, 1%, 1.9% iron oxide result. Nothing to write home about. What else? It's got copper on laser ablation. So we'll see if there's anything going on there. We've got nothing there. We've got manganese, 159 parts per million. Yeah, so that's sort of how the results are stored against the geological feature. And what will happen is that as you get more results connected to these geofeatures, you can see that this is a feature here, the Burstal suite. It's probably got about 6 sets of data. In reality, you'd have hundreds and hundreds and hundreds of results against these things. So you couldn't look at it like this. But what we can see here is that if you get enough, you can write queries and actually infer that because all of the iron oxide XRF results are above a certain threshold or a certain set of rules that you've applied have been met, then you can actually assign a geological property to this Burstal suite. And that geological property can then relate back to the mineral system. So I've got a bit of an example of this here around the iron oxide stuff. So this is just a cut down version of that same graph. We're looking at the exact same thing. I've just pulled a ton of data out of it and created a subgraph. So here is our mineral system, and we're only going to be looking at the one ingredient type, which is a highly desirable ingredient of reductants. Okay, and for those reductants, there's a few options. There's being alkali feldspar rich, there's carbonate rich, silicate rich. Here we've got iron oxide rich. Okay, so iron oxide rich being one of the geological properties that satisfy this ingredient for this mineral system. Okay, and then off of that iron oxide rich, because of the results from these XRF values for, say, the double crossing metamorphics, since the XRF values are pulling reasonable numbers, so we've got 12% iron oxide, which is not too bad. And then I think there might be a few others which are pretty high. 13.6% iron oxide. We can say, I'm no expert in this. I'm just looking for good examples to explain this concept through to you. But so that we can say, oh, this is an iron oxide rich geological feature. So we assign that property, and that property then connects to the mineral system. So then you can follow that and traverse those things, write queries to pull back all of the geological features that meet this certain criteria, or you can infer and impute these geological properties from the results of your data, and then generate, and start forming those connections to whatever system models you've put in alongside of your geological settings that you've created. And that sort of comes down to, that sort of covers the main applications of setting it up this way. And as time goes on, as you introduce more data, for example, our geoproperties database that we are working through and adding more and more data to, will be able to work like this, where you're adding more results into the system, and then you can continually, as you add more results, you can continually start to generate these sort of properties out of the data, and then able to start forming connections and seeing where things can connect, and get insights that way. So that sort of covers what I wanted to talk about around applying semantic modeling in a more formalized approach to geoscience and geological settings. It's obviously it's a lot more you can do, and I'm still, we're all still learning. I'm still learning through this as well. It's a growing area, especially with the ability to churn through data so quickly with the use of AI, but then the risk of getting bad data and sort of spiking the data set with poisoning your data set. You really want to use good quality stuff, especially if you're spending all this time putting it together. So anyway, wrapping up, just want to talk about, we talked about label property graphs. So they offer that low risk, fast time to value in terms of data mining. Really useful. Get all your data together, query it. Very useful thing for getting that nudge in the right direction. Might get some insights, and obviously it's got AI written all over it. It's strong use cases in terms of being accelerated with AI, and also accelerating AI. So it can also be used by AI to improve things. So there's a bit of a symbiosis between labeled property graphs and AI, and you'll see a lot of that coming up in the future. In future developments, probably in apps and things that we use every day. And then we also talked about semantic modeling, so RDF triples. Obviously, they have a higher development effort. You can see how much goes into getting the framework right and all the labels right. So there's a slower time to value, but the use case is you get precision, which is really, really important in geoscience. You get interoperability, which is once again very important because you're working between academia, governments, industry. You want that interoperable data. You want to be able to reuse it as well. If someone's collecting data and just sort of sits around, you want to be able to reincorporate it into a future system. If you're adopting the same ontologies and models, then you can reincorporate data from that's been archived. So yeah, it's quite, it can be used for describing geological settings, and probably lots of other areas you can use it as well. It's just that there's just so much work in this space that are really focused on applying it to geological settings and incorporating factual real-world data. And it's also quite interesting to see how it can be used to look into system modeling too, just like mineral systems. I don't know too much about mineral systems personally, but there's quite a few people in GSQ who have that capability, and it's really good to work towards finding different ways to apply this formalized modeling approach to bring data together, whether in knowledge graphs, whether it's through labeled property graphs or semantic modeling. You can put all sorts of data from different contexts together and get insights in ways you hadn't been able to in the past. Yeah, if you want to talk more about this stuff, we don't have too much content on GitHub as yet around knowledge graphs. I do plan to put a lot of this stuff up on GitHub before digging deeper comes up, just so that they've got that content there to refer people to. and I'm doing a little talk about this stuff at one of the separate workshop sessions, not as in-depth as this. But yeah, if you want more information about knowledge graphs, always happy to talk about it, and you can get in touch with us through that inbox there. That's a fast way to get through to me. And yeah, thanks for your time and listening, and hopefully you got a bit out of that and can take some of it forward for your own knowledge graph investigations.
Thanks so much for that, Steve. We do have time for questions now. So if we do have any questions from the audience, please use the Q&A box or the chat, or use the Q&A box, please. I guess one thing I'd like to point out there, working on this, is I know sometimes we have skepticism around AI, particularly in geoscience, and its ability to look at what are quite biased samples. And the thing I really like about the RDF triples is it's not like a black box that, a conventional neural net that you put data into and you get results out and you can't work out where the connections have happened, but you can go through the entire knowledge graph and work out, oh, it thinks this is this and it thinks this is this, and then you can go back and you can change assumptions, or you can check what the assumptions are, as opposed to a CNN, which are nearly, you put the results in, you get a thing out and you're not sure if there's hallucination in there or there's other results in there. So I think by building these vocabularies and by building these knowledge relationships or graphical relationships between our data sets, we reinforce the ability for AI to make more accurate understanding of our data. Would that
makes sense? Yeah, I think it's a bit like that cybernetic approach. So your robotics, for example, which is very much control. It's full control over a piece of mechanical equipment, and you sort of see the RDF formalize stuff as a machine, and then they put that AI layer on top of it. So say how you get robots can then interact with people, but the underlying stuff is tested and precise, so it doesn't break glasses when it does. If the robots can do the dishes for you, it's not going to smash all your glasses, because all that stuff controlled through solid formalized systems.
I don't see any questions in the Q&A yet, but I wrote down a whole pile of questions. So the coal example that you showed early on, where you had the linkages between different described rock units. I was thinking to myself that what a geologist might do out of that, if they were trying to then derive their knowledge, would be to turn that into rather than a bunch of connected nodes, they would turn it into a stratigraphy diagram, for example. And there might be something, that a property that would go away and maybe give them or otherwise regarding how thick to make those relatively thick, whatever. Are there tools that are doing that? Or are you guys doing that, or are there tools that are turning the? I guess it brings to my mind one of the things that's important in these things, which is to get geologists to use this really powerful stuff. It's got to be taken from the way data experts look at it to the way that geologists look at it. And I was wondering if you guys are thinking about that, or whether there's work already underway with you or others to take this to translate the three-dimensional knowledge network diagrams into various sorts of things that geologists usually use as a shorthand to visualize some of these relationships.
Yeah, so probably best done through the formalized modeling using RDF, and that's sort of how we've structured the data model, combining our factual data, our results and samples and observations against particular geofeatures. So for example, if you had a particular formation, the properties of that formation could be in there in terms of the thickness or the thickness range. That can all be spelled out, and then from that yes, there it can be. You can produce those types of visualizations. I probably wouldn't go generating them out of the labeled property graphs, the more open schema types, because it might just get a bit haywire and less reliable. But if you start from the RDF style, the formalized semantic modeling approach, yeah, we're building that up now, and we're working on some proofs of concepts around the Manweiser area to represent some of our geological features in that way. So producing maps, so GeoJSON characteristics of these geofeatures that you can put onto a map, but stored in a graph. I think that's, yeah, we've got some demos of that on one of our vocabulary servers that does that. I think it's used this thing called GeoSparkle is the language, which is a geospatially connected Sparkle querying capability. And we've got some high-level geological features around Queensland set up there where you can sort of see how that would work. But nothing so far offhand around generating, a quick stratigraphic profile. But once you get it into that format and you have enough data there, it's not out of reach. Yeah.
There is a question that's just come up, but I guess I'd like to just add to that point there. The converse is really interesting as well, that we might be able to use strat columns from reports or time space plots to start defining relationships between features. So using the graphical information or the pictorial information and using that to derive better understanding of the relationships between units or formations and how they fit within the geology. But there's a question here from Andrew Paul. What scope is there to create your own edges? When you consider there are two classes that are not linked but should be, can you edit it, or do you add in the documents for the process to read it, if this makes sense? And how do you keep such insights in your model? Can you use that, Steve? Or
yeah, I can see the question. So creating your own edges, yeah, you can just add them in as long as there's an edges has a source and a target. So as long as there's as long as there's a node for the source and a node for the target, you can generate your own. If you're getting into this, if you want to sort of manually work with data and knowledge graphs, there's a really cool software application called Cytoscape out there. It's an open source tool, and it's used for graph visualization, and you can work with CSV files. And if you want to get sort of manually grind away at the data, then that's a cool tool for changing the data around and seeing how it works. And the other part of that question was, how do you keep insights, any such insights in your model? Right. So I guess if you're imputing that edge, or if you're creating an edge that's not part of your source data, you might want to have it a bit like a database view, as opposed to so a view of your data, not your actual master graph data. If that insight is not, if it's a created edge that's more around you just linking it because you think these two things are linked, but you're not sure. So that could be, you'd have to have it as a separate data set. You probably wouldn't build that into, or if you were to put it in, it would need a property to say that it's kind of inferred or not, not something that has been authoritatively placed into the graph.
sorry, dropping things on my desk. There's a question here from Jenna McGovern as well. Really great talk, Steve. I may miss this already if you already discussed it, but are there any constraints around how recent or well-cited data and reports should be when investing data into these tools? ROP descriptions and results from analysis and our understanding of mineral systems has evolved so much over time. Is there specific logic around deciding how much variability interpretation to include when curating data for this?
I'd include as much as you can. So when you, we've had some other talks, I think, previously around the CCAN API, but our geoscience data repository, our geoscience data got curated over the year, the open data portal for GSQ, has an API where you can access all of the metadata against the resources and packages. There's a lot of information there. It's classified by earth science data categories. There's report types, and you just put all in there as you can. Obviously, when I do demos and things, I don't want to put it all in there because it becomes too noisy. But yeah, there's a whole bunch of metadata you should add in. There's no reason not to include it, especially if you're doing it. You're not doing it in a visual way. If you're doing it as a database, it just goes into the graph. You don't have to look at it. So you're just querying it, and it's good to have it in there. And because metadata is graph by nature, so you can definitely throw that in there. I'm just having a look at the rest of the question. Variability and interpretation when curating data sets for a label property graph. There would be, yes, and it depends on the AI model you use, or the person model, the human model, or you can, before you go about it, you might want to set some rules for the AI or the person who's going through the text to determine how things relate, for sure.
Okay, I think Matt's had a bit of a crisis come up with a pickup. But I've gone through the process of offering promotion to panelists to those who wanted it. Not everybody wanted it, but Steve, you had your hand up, Steve Micklethwaite.
Sure. Hi, everyone. It was actually going back to your point, Rick, around turning the knowledge graphs into information that is more easily understood by geoscientists. So in the Loop project, which is being run by Mark Jessel, they've already done the converse. They've already turned geological maps into knowledge graphs in order to extract sequence information. So that code is out there and has been developed, and I think you could probably take advantage of that. And then I had a question, because here at SMI we have been using network theory in the risk space, and in another we're looking at mineral systems applications as well. And those are for digraphs where you have directed links between the nodes, so there's a logic to it. But the point there is that there's lots of topological metrics you can use to check the quality of the network. And I was just wondering if whether that's something you do here, whether you use topology metrics, and also whether it be something you'd be interested in.
Definitely interested in it. We would be applying shapes constraints language to build out those validation rules to validate the graphs that we're creating. So we're starting to play around with that a lot in terms of we're working with geochemistry data, and we're taking geochemistry data out of a spreadsheet, converting it into an RDF, and applying shapes constraints language to validate the contents of those spreadsheet submissions to see if they conform with the rules that we have against our vocabulary. So that's how we'd be controlling the quality and the precision of what goes in. But that's about as far as we got there. We definitely have scope to add those quality aspects. I think it's essential if we're going down the path of this formalized approach of doing things. We need to get full benefit out of it and tap into all the precision tools that we can take on. But yeah, I'm interested in that Loop project too. If you got any links to throw up, or
I'll have a look. Matt knows a lot about it as well, so the survey is connected to the program.
Oh, great.
Yeah, there'll be some good stuff on that, and yeah, so I think that'd be really good. The one thing I was going to say was that I feel like in the last few years I've kind of taken my eye off what's going on with all of this, and been doing whatever the hell it is I do these days, and it really feels like things have gone ahead in leaps and bounds. So many of the words and the things you're doing are just now have suddenly become, if not completely foreign to me, then certainly not familiar. And I don't know, I guess I had two questions. One is, are you guys out ahead, or is your perception that this is where the world is these days, amongst surveys and companies and that sort of thing? And so that's part one of the question. Part two of the question is, I see that there are quite a few exploration people on the call, or on the webinar. Is what sort of training resources can you recommend for people to catch up on all this sort of stuff, or is there a need for training to make sure that people use the kind of rich set of new kind of things that you're developing as part of all this work?
Right. Well, in terms of being out and ahead, I think GSQ is out and ahead on this front. It's been working on this for a couple of years, or 3 or 4 years now, actually, and getting this framework in place. And other jurisdictions are picking it up and also heading down that path around Australia. But yes, definitely out ahead on the formalized RDF style. We have our vocabularies up, being hosted, and able to be used, and they're connected to our online lodgement systems. Our systems applications are relying on these vocabularies that we're setting up. So yes, out ahead in that space. Probably in the label property graph space, I think that's been going along heavily in other industries, maybe not as much in geoscience. So I think we're not out ahead on that in geosciences yet. I think a lot of the hesitation around label property graphs is that there hasn't really been a non-proprietary standard. It's mainly been that Neo4j being one of the top databases used, and they have and that gets me to the answer for the next question, which is there's a whole, in terms of label property graphs, Neo4j have a great range of tutorials. Because they're a company and they want people to understand the graph, so there's a whole range of information there, and it'll probably lead you to some information around that GQL standard that's just come out as well. So yeah, Neo4j has great materials. There's probably a few other, I think it's called opencipher.org, I think is the language that they use to query the labeled property graphs. And in terms of the more formalized approach, RDF, it's a challenge. I think there's a few YouTube channels I think that I've used to try and catch up on it, but everything's written in standard, like on W3 standards. If you can go through, if you're used to reading standards, or I think over Christmas I went through a lot of these things because it takes a bit of time to read through the really formalized technical documentation around how these things work. But if you want sort of the one pager, you probably won't find it in the standards. You're better off using an AI. So just chatting, because the thing is that all of these standards have been around for 4 or 5 years, and they've been ingested by the large language models. And so because they're open source information, complete information in the W3 standards. So when you talk to any of your large language models and ask it questions about graph technology, then you're going to get pretty good answers. And I think I've done most of my learning on these matters through talking to AI about it, because it's trained on it already and it has access to a complete set of standards that referenced. And I don't think, because it's not that it's not used in commercial media, it's not used in other types of things, marketing, advertising. It's not really heavily promoted. It's a bit of a backward area in terms of the web content. It's pretty clean data. So once you talk to an AI about it, I don't think it's going to be that far from far from the truth, so to speak.
Do you have any other questions from? I have more, but I don't want to monopolize in case anybody else has any. Oh,
I had a little bit of a follow-up question, if I can, Steve. I really, I've been doing a little bit of dabbling in geology relevant AI, and one of the things that keeps coming up for me is, LLMs hallucinate. When you even if you have something like what you've presented, which has a lot of very industry specific knowledge, can you maybe talk to how specific do you think we have to keep things for the information coming out to be accurate enough for geologists to want to rely on it, I guess?
I don't know if you can rely on it. You can definitely get a hunch or a lead or an idea. I don't know if you'll ever get to that point to rely on it unless you're using an agent, probably an agent model. So not just the one AI. So rather than just going to an AI saying, "Hey, look at these documents and tell me what the go is," you might want to have multiple AIs in the pipeline where they're working together to find out the right information, and the last one at the end kind of runs a set of checks or runs the result through a validation mechanism and does that kind of check for you before it releases it out of the system. So you sort of need like a QA, quality control, like in a factory or anything. You have quality control people inspecting goods before they get out. Each step has its own role. You can't just, I think just one-shot AI for this purpose is not, I don't think it's going to give you any confidence. If you want to increase that confidence, you'll need to have different AIs with different capabilities working to solve your problem. You have to wait longer, maybe 2 or 3 minutes to get an answer, but at least you're not getting crap. And I think it happens like that with code. I think some of the latest stuff will actually try running code and testing it before it sends it back to you to make sure it works. So they don't give you bad code as well. So, I guess geoscience, we probably won't be the first to get the capability. It might be probably medicine or something like that. They'll have a similar capability that we could possibly leverage. Rob's put his hand up. He might be able to add to it.
Yeah, and it's really great that we have the SMI on the call, because one of the things Steve and I have been talking about, it would be great, whether it's an agent or just to have a repository of geoscience knowledge, or if you're exploring in Mount Isa, like one of the atlases or the text of geology of Queensland, if you could somehow translate that knowledge into a knowledge graph, then some of these graph-based AI tools could use those to help get the right answer versus just completely make it up. But I don't think anyone's doing that yet. So.
Thanks, Rob. Does that answer your question, Jenna, or to some degree?
Yeah, it does. I mean, yeah, agents are the future, I think. So that's good to hear that that's sort of the direction it's going. I really like how your LPG actually played out. Everything did look like it made a lot of sense. It looked like there was a lot of experts in the know behind that compared to what I've seen pumped out more generally before. So I was pretty impressed by that.
Thanks.
Do you actually have plans to? I mean, I really liked Matt's suggestion of working the other way rather than generating maps, images, or stratigraphic sections or something, to actually extract insights in terms of the edges that you're talking about, to be able to try to do that. Is that something that you see? Are there plans to do that as part of the work that you're doing in this area, or is that? Yeah,
definitely. It aligns with our strategy of getting more value out of our data. So that's we have that enormous bevy of information in the portal, and a lot of that's untapped. And all those appendices, we've OCR'd a ton of text documents, but it's just the main reports. There's also the attachments and appendices and CSV files that go with those data and data sets. They all need to be brought into something. So yes, definitely it's on the agenda. It's just a huge undertaking, and I think where we're at the moment is looking. Rob can probably talk more to it, but we're looking at grabbing data out of the tables, the table extraction from tables and reports, because there's a lot of good stuff in those tables. Maps might be a bit harder. The stratigraphy diagrams, I look at them sometimes. I think that's amazing. There's so much information on that thing, and it has all the events as well, like the different orogenies or whatever that's happening along the way. Being able to bring that into a machine-readable form and bring time into the equation, it seems really powerful. It's just a matter of how do we get it off there and how do we get the data model right.
Yeah, it's funny. I was thinking about as we were going through this. I don't know if anybody on the call's a fan of Hitchhiker's Guide to the Galaxy, but I think Douglas Adams in one of his books said that there are, depending on your age, there are 3 different things. Things that were around when you were born, which are basically part of the fabric of the world and always existed in your own mind. And then there are things that developed at an early stage in your career, which are, which you feel are really, really cool and probably, be something that you should learn about and then use in your professional life. And then there are things that are developed in the later part of your career, which are against the laws of nature and should therefore be banned. And asking an AI to teach you how to I'm not saying it should be banned, but I'm just saying when you said, well, the best way to learn how to do all this stuff is just to go to the AI and ask how to do it, because it's mapped it all already and learned it all. And that as a concept is completely foreign to me. So learn something new today. But it was really, to me, it was really interesting and really great to see an update on what you guys are doing. And my mind's kind of racing, trying to think about how do I, but all the other people who want to actually, who want to use these sorts of advances to streamline our activities, the activities of people who are actually out there trying to work with hundreds of reports in their areas or something like that, to use this new, I guess the new way that the whole data is being structured and analyzed to make their activities more efficient. So it was a really, really interesting and insightful seminar. I guess, Evan, have I got it right that we're sort of closing up somewhere around 4? Is that right? I certainly have something I have to go. I have another engagement at 4, but was that the plan? Or
yeah, we can keep going longer if there's discussion warranting that, but it seems to have quietened off a little. So yeah, perhaps maybe this could be the last call for anyone who has a burning question or point to discuss. But yeah, we can keep going if we need to, but yeah, 4 o'clock probably seems okay to me.
I've got it. Well, I do have another one, but I'd be really keen to hear if anybody else has another question as well. Turn this off. I was talking to one of our partners yesterday, and he's working in a brand new area. He's got a great opportunity with a partner who's with a JV company that they're working with in an area where there's a lot of potential. There hasn't been a huge amount of exploration, but there are 700 exploration reports as a resource that that haven't been looked at or worked on by anyone so far. They're not even digital yet. How would you recommend that they do the most efficient job possible of taking that sort of resource and turning it into something that they can, using new tools to allow them to get to important exploration insights more quickly? Pretty
well, I think
question to ask with 5 minutes to go, but
you'd start off with cataloging. So you'd obviously, if they're not digitized yet, you would get them digitized. So there's tools online. All cloud providers have services that do that So that's an OCR type tool, like text. AWS has one called Textract, and Textract offers different tiers of looking at information. So you can just grab text and OCR the text out, or you can also pay a bit more. It'll grab table data as best as it can, and if I think there's also a higher price as well if there are forms, or if there are forms in the data set that you're looking at, say there was submissions or applications for things, and they're laid out like a type of form, then there's features to grab the form data out as well. So there's that process, so the OCR cataloging. Then you want to index it, create your own index. You can create. There's a tool called Elasticsearch or OpenSearch, or any of those search tools. I think they're the ones I know off the top of my head. Amazon, AWS. We use AWS for most of our stuff. Pretty much all of our stuff is AWS. There's one called OpenSearch, and OpenSearch is a simple way. It's a document database. You just shove documents in there with metadata. So, and then you have your text field that contains the text that you just extracted, and that will be able to search that. And if you find that a bit complicated, too many steps of the way, there's even tools out there, whether it's through AWS or any other provider, that can just ingest the PDF documents and do all that automatically in one big hit. So AWS have one called Kendra. It's been around for quite a while. You just put all the data into a bucket. I think you've heard of S3 buckets in AWS. You just dump the data. So you just point the thing to that bucket, and it'll go ahead and generate that index. So that's where you need to kind of make the data come alive. So get it out of that dead, stale place into a digital active space. And then from there, you'd want to start data mining it. And whether that's you could start by using what Rob talked about last webinar around setting up a chat tool, like a RAG system. So where you can ask questions, and then it'll go and search that index, that database that you created over that data, pull it back into context and start answering your questions to give you some insights. Alternatively, if you had the time, you could generate some sort of property graph and go down that graph RAG approach. And also just statistical analysis as well on, sorry, my lights just went out. Been sitting still for too long. Statistical analysis on the text as well, and finding out key themes. Something you can also do with the text content is not only when you're generating your metadata off those reports, you could also create small digests and summaries and try and compress your information, because some of it might be not worth looking at. If you've got images, there's tools to look at images. I'm not sure how good they are for geoscientific images, but they're good for picking out cars and traffic lights. I know that, and bikes and buses. But the other, geological type things might be a bit challenging to go any further than that. And then I guess you've got to set up a database of some sort. So not just you've got your index, but then you want to start building out your own database, and I'll probably start with an open schema until you start seeing the patterns coming through, and then maybe start locking it down from there.
Thanks. Yeah, no, that's good. Well, there's another question now from Derek. Read the tools point. ArcGIS Pro has some inbuilt functionality to pull spot observations out of a map image. Loop 3D also has some code to extract info from maps, including fault network topology. I don't know many people using this capability in conjunction with knowledge graphs would be a great area for research for some honor students. Thanks, Derek.
Thanks, Derek. Yeah, that's awesome. I'll have to look into that.
That was really good. I have to run out. I have another meeting now, but thank you very much. Thank you very much, Stephen, for the presentation. I thought it was fantastic. Really a lot of food for thought there, and congratulations on the progress you guys are making.
Thanks, Rick.
Thanks everyone for coming along. Quite a few people have pulled out already. There was a larger amount earlier. Thanks again, everyone, and thank you, Evan.
Yeah, thanks. Just one quick bit of housekeeping as we wrap up. Thursday, the 12th of December, we're having a webinar on the Collaborative Exploration Initiative. So there'll be some information about round 9, as well as some case studies from some previous recipients. So we'll send some comms out about that one shortly, Thursday, the 12th of December.
Great. All right. Thanks very much.
Thank you.
Thanks, everyone. Bye.
Yeah.